Alright, so let's look at these. These are now simple supported beams. Again, shear force and bending moment diagram. This is a pretty simple one. If we were to write functions for this one, how many sets of functions would we have to write? Well, we'd have to write one set that goes from 0 to L over 2, and another set that goes from L over 2 to L. That would take some time. Watch how fast we can do it with this graphical technique. Again, sparing you the details of the reactions, I will tell you that this reaction is P over 2 up, and this reaction is also P over 2 up. So starting with my shear diagram, what kind of shear is this? Positive or negative shear? That's positive shear, equal to P over 2. What kind of shear is this on the right-hand side? That's negative shear, minus P over 2. So again, I know where I'm starting, I know where I'm going. We'll write the expressions again. Change in shear is the area under the load diagram. So looking at the change in shear from 0 to L over 2, I'm not going to consider this yet. Let's just look at this first piece. So over the first section, what's the load? 0. So that means there's no change. If I start at P over 2, I should end at P over 2. According to my differential relationship, the slope of the shear diagram is equal to the load. And we already talked about our load being 0, so that means all across this section, 0 slope. So the first half of this beam has constant shear equal to positive P over 2. Now, as I move from the left side to the right side, how much does my shear change? It changes exactly this P value. Is that a positive P or a negative P? Negative. That's negative because it's down. So if I go from P over 2 and I subtract P, I get negative P over 2. So you notice the change in shear here is P, and it's negative P, and that matches the applied force. So now the change in shear is the area in the load curve between L over 2 to L, and the load curve is 0, so no change. So if I start at P over 2, hey, I hit P over 2. Great. It also tells me the slope of that curve is equal to the load, and we already said the load was 0, so that means the slope is 0. So the second half of the beam has negative shear equal to P over 2. Pretty cool, huh? Well, let's do the moment. So let's start the moment. What do I know about the moment? Let's go up here and look at the moment. What's the moment at this external pin? 0. What's the moment at this roller on the right hand side? 0. So now I know that the change in moment is the area under the shear diagram. So looks like the shear diagram is continuous for this first section, L over 2. What's the area of that curve? Well, it looks like it's positive area. Base times height, that's PL over 4. So you take 0 and add the change, you get PL over 4. And what's the shape of the curve here? Well, according to our relationship, the slope of the moment diagram is equal to the shear. And what is the shear everywhere in that? Well, it's constant and positive. So I have a constant positive slope. In fact, again, if I checked it, it would be equal to P over 2 to 1. So now in the second section, what's the change in moment? Well, it says it's equal to the area of the shear diagram. Well, what's the area of the shear diagram there? Well, it's negative. Again, it's a rectangle, so base L over 2 times height negative P over 2. That's negative PL over 4. You start with PL over 4, subtract PL over 4, you get 0. Yay. What's the slope of the line here?
Constant.
It's the shear, and the shear is everywhere there. It's the same value, and it's negative. So again, this would be now negative P over 2 for the slope. And then you can see your moment diagram tells you what's the maximum moment. It's PL over 4, and where does it occur? Right in the middle at L over 2. So you would design your beam to handle a maximum moment of PL over 4 and a maximum shear of P over 2 at the ends. Now you have all the characteristics you need to design your concrete beam or reinforced concrete beam or steel beam. Let's do one more. We're going to start with this one like we did before. We'll get the concentrated equivalent force. It's a rectangle, so it's base times height. So that would be W naught L. And if you look at the reactions on both sides, they're going to be up. And they're basically going to be this load divided by 2. So I'm going to start off at WL over 2 and end over here at also WL over 2. So again, starting at the left-hand side, we always go from left to right. What do I know the shear here? Well, according to this, the shear is up, which is positive or negative? Positive. So this will have a shear of positive W naught L over 2. And I know the shear here. What's that? Positive or negative shear? That is negative shear. Negative W naught L over 2. The change in shear is the area of the load diagram. The load diagram is continuous across the whole structure. What's the area of that curve? Well, it's a rectangle, so it's just base times height, W naught over L, and that load is positive or negative? Negative. So if I start at WL over 2 and subtract WL, I do in fact get negative W naught L over 2. And the slope is given by the load, and the load is what? It's constant, and it's negative. So you get something that looks like that. What's that right there? That's where the shear is 0. Does it really occur right there in the middle? It does. So if you were to project that up, what's that saying is that this area under this part of the curve changes the shear. So you subtract that area from here, which is half the load, you do in fact get 0 shear. So this beam has no shear right in the middle. So what about the moment? Well, again, starting at the left-hand side, we like to go left to right. So left-hand side, what's the moment here at the pin? I think that's 0. And the right-hand side? Also 0. I know the change in moment, it's not a flat line, is it? No. I know the change in moment from here to here is the area under this part of the curve, shear diagram. And what is that area? Well, that's a positive area. It's a rectangle, so it's 1/2 base, L over 2, times height, WL over 2. So that should be WL squared over 8. So that means I should end up here at W naught L squared over 8. And what's the shape of the curve between these 2 points? Is it a straight line? No. What's the slope of the curve right here? It should be equal to the shear, and the shear is a big positive value. And it decreases to 0. That's a 0 slope. So this is a curve of order n equals 0. This is a curve of n equal 1. This should be a curve of n equal 2, so it's quadratic. So you're going to get a shape that looks something like this. That's half of a parabolic shape. Now what happens on the second half? Well, the change in moment between these 2 points is now the area under this part of the curve, which is a negative area. It's a triangle, so 1/2 base, L over 2, times height, minus L over 2. I don't know what happened there. That should be a 2. So that ends up being negative W naught L squared over 8. So when you subtract that from here, you get 0. The slope of the moment diagram is the shear. The shear starts off at 0 and increases to a large negative slope. We start off with a positive slope, end up with a negative slope, and then you connect that, you get this curve. So this is the distribution of your moment. What's the maximum moment in this beam?
WL squared over 8.
WL squared over 8. Where does it occur? Right in the middle. Here's something to notice. It looks like the maximum moment occurs when the shear is 0. Because 0 shear means the slope of the moment diagram is horizontal. And usually max or mins dip down and have a 0 slope. So this is going to be a new characteristic that we're going to spot. Every time we see 0 shear, it's going to indicate that we have a 0 slope on our moment diagram, and that might be a local minimum or a maximum. Now you're probably looking at this and say, well, here's our maximum. Do we have a 0 slope there? Well, we kind of do. It's right here in the middle. Because as you move from this side to this side, it goes from positive slope to negative slope. It does have to go through all that. So it's not a 0 slope, but it is a change which indicates you're peaking and then dropping. That's another possibility. Okay, I'll try to give you some of these to work on that are slow and steady and not so bad. Because I imagine you guys won't even, oh, I better stop talking and come to stop.